Hi folks, and welcome back to Physics with Captain Rod. I'm making this video here to provide you with examples of how to write Newton's second law equations. So when we take a look at this here, all right, example 2, assuming a generic acceleration, meaning it could be in 2 dimensions basically, write the Newton's second law equations for each free body. Assume the free bodies are complete. All right, so the first thing we're going to do here, we're going to take a look at this free body diagram right here, and we're going to assume those are the only forces acting on it. Now, one of the things I always recommend students do is this. When you're dealing with free bodies and writing Newton's second law equations, a pretty good rule of thumb is to identify the acceleration direction, if you can, and call that positive. So when we write our equation here, no doubt looking at the picture, this is going to accelerate to the left. So we're going to call that positive. Now remember, Newton's second law says, all right, the net force acting on an object is equal to mass times acceleration. And remember that Newton's second law is a vector law, so you apply it by direction. And the net force acting on an object is the sum of all force vectors acting. So if we apply that here, if we sum up all forces in this direction, that has to equal mass times acceleration in that direction. And we look at our free body, there's just 2 forces. So if we call left positive, F1 minus F2 would be the vector sum of these 2 forces. And then the rest of it would be equals mass times acceleration. And this is done for this example, and there's nothing more to chat about. All right, moving on to the next example here. All right, now this one is a 2-dimensional problem. And we can kind of handle it a couple of different ways. One, we could find the net force first and then write a force equation in that direction. Or we can do this, all right? We can apply this, all right? Newton's second law, force equals mass times acceleration. We can just apply this equation in both directions, all right? And I'm going to go ahead and choose that approach, and here's what it would look like, all right? So if we add up the x components of all force vectors, and I'm going to go ahead and call right positive, that would have to equal mass times acceleration in the x direction. So what we're doing here is we are applying this equation in this direction, right? So vector equations are applied by direction, right? So when we look at this picture, I'm going to write the equation out and then talk about where these are coming from. That's going to be F1 cosine of the angle theta plus F2 cosine of the angle alpha is equal to mass times acceleration in the x direction. All right, let me go back and chat where they're coming from. Right, when you look at force vector 1 here, it has an x component and a y component. And that x component is adjacent to that angle theta. If you run through the sines and cosines, that's why you end up with F1 cosine theta. Similarly, force 2, drawing it in component form, well, that's kind of a crummy picture, but I'll just leave it as is. The x component is adjacent to the angle that I called alpha. And F3, oh, and I forgot F3 in that equation here, so I need to add a minus F3 right here to take this into account. So let me write that so it's a little more legible. So F1 cosine theta, it's positive because it points to the right, plus F2 cosine of the angle alpha, also positive because it points to the right, minus F3, right? No sines or cosines required because of the direction. It's negative because it's pointing left, and we are calling right positive. Then the rest of this would equal mass times the acceleration, but we would we would be talking about just the x component of the acceleration. All right. Now we can write an equation in the y direction. If we add up force components in the y direction, that has to equal mass times acceleration in the y direction. And I'm going to go ahead and call up positive for this. Oops. There we go. All right, so looking at this picture, this force vector, which is opposite theta, is in the y direction. So we're going to have F1 sine theta. This force vector, which is opposite the angle alpha and is down in the picture, that one's going to be minus F1 sine alpha. And then this force vector does not have a y component. So if you want, we could put a plus 0 there just to say that we at least considered it, or you could leave it blank. That's it. Right. Equals mass times the y component of the acceleration vector. So there's Newton's second law applied to this free body, kind of assuming a generic acceleration that has an x component and a y component. I hope that this video helps. Have a great day.